Very good morning, everyone. Can you see my slides? Can you see my presentation?
Yes, sir.
Can you
Yes,
see?
sir.
Okay. So if I remind you, we are here. We are discussing molecular orbital theory. We have discussed the basic postulates of molecular orbital theory, and these are the rules for linear combination of atomic orbitals. Right? You can say these as rules for linear combination of atomic orbitals. Let me write it in full form. Linear combination of atomic orbitals. We have already discussed what we mean by linear combination. By considering two atomic wave functions, we have seen it, what linear combination means. When we are talking about linear combination of two atomic orbitals, you consider both its symmetric combination, combination of atomic orbitals of similar symmetry, both are in same symmetry, and another combination who are not in same symmetry. So symmetric combination, dissymmetric combination, and both leads to symmetric combination leads to formation of bonding molecular orbital, and dissymmetric combination leads to formation of anti-bonding molecular orbital. And we have seen it like this. When we say linear combination, let us say, for example, two atomic wave functions of two atoms. Psi A is the wave function or atomic function of atom A, and psi B is the atomic wave function of atom B. When both of them undergo linear combination, that means we need to consider positive and negative combination, additive and subtractive combination. When both atomic orbitals are in same phase, that will be positive combination. When they are not in same phase, it will be subtractive combination, and this positive combination will lead to formation of bonding molecular orbital, and this subtractive combination will lead to formation of anti-bonding molecular orbital. Right? So then, whatever the rules of linear combination of atomic orbitals we have already discussed. Just by taking an example of drawing a molecular orbital diagram, for a general diagram considering a molecule AB, how to draw a molecular orbital diagram. Drawing a molecular orbital diagram. You must be thinking, what is this molecular orbital diagram? See, what are we discussing altogether? We are discussing how atoms are combined through covalent bonds to form covalent molecules. So we are trying to understand through this molecular orbital theory, we are trying to understand how atoms are combined to give you covalent molecules. There are two theories to understand this. One is valence bond theory. We have already discussed that. Yes, that theory is having certain limitations, major limitations, which failed to explain formation of certain molecules. Then we came to molecular orbital theory. This is a widely accepted theory because this explains most of the properties of molecules. So now we are going to see how atoms are combined. Their atomic orbitals are combined in form of a diagram. That's called molecular orbital diagram. Why molecular orbital? Why this term? Because if you look back to linear combination, rules of linear combination of atomic orbitals, or basic postulates of molecular orbital theory, that says atomic orbitals of two different atoms having similar symmetry and similar energy, they undergo combination, linear combination, to form molecular orbitals. So what are we going to see now? How molecular orbitals are arranged. Like we have seen, atomic orbitals are arranged in an atom. Similarly, we are going to see now how molecular orbitals are arranged in a molecule, and how molecular orbitals are formed because of combination of atomic orbitals. This whole picture we are going to get in form of a diagram. And let me tell you, the diagram is nothing but a plot between internuclear distance of separation between atoms versus energy. Look at this. Just let me draw. It's like this. It will give you more clarity. I need to reverse this. Look at this. I can say like this. This is internuclear distance of separation. This is just a plot. Nuclear distance of separation. Internuclear distance of separation. And here we have energy of orbitals. Although in books you do not find, wherever it is plotted, you do not find this. For your understanding, I am showing this one. This diagram is nothing but a plot between energy versus internuclear distance of separation. What is this internuclear distance? Look at this. What we are talking about. We are going to demonstrate how two atoms are combined to form a molecule. We are going to understand how atomic orbitals are combined. So these are atomic orbitals of two different atoms. One atom on one side, another atom on another side. How they are combined to give its corresponding molecular orbitals. That's what we are showing. So this is what is the separation, distance of separation between between two atoms. So that's what is called internuclear distance of separation. And this is energy. Why? Because this is one atomic orbital. Another atomic orbital will be arranged like this. Like this, it will go on. And these atomic orbitals of one atom will be arranged as per increasing order of their energy. Similarly, on the other side, corresponding atomic orbitals of similar symmetry and similar energy will be arranged like this. I will show you later on. We are going to now see, this is a general example I am showing. Next to this, we are going to pick up specific examples starting from hydrogen molecule. That will give you more clarity further. So this is two atoms, one atom A, another atom B, and psi A is the corresponding atomic wave function or atomic orbital of atom A. Psi B is the corresponding atomic wave function or atomic orbital of atom B. They are combining. And let me tell you, this atomic orbitals of similar energy, that is why you see, look at this, they are in same line. This is not about beautification of diagram, how the diagram looks more attractive or more beautiful. It's not that. It has, these atomic orbitals are in same line because they are of same energy, similar energy. That's what our rule says. Orbitals of similar energy and similar symmetry. Symmetry, I have told you. Look at this. This red color is of one orbital. This blue are of different orbitals. We can say it's a p orbital. So if I want to combine them, these two orbitals need to have same symmetry. What do I mean by symmetry? Let's say if I put it here, these are not of same symmetry. They cannot combine. Combine means overlapping between two atomic orbitals are not going to be effective. If overlapping is not effective, that is stronger. So this is not going to give you a formation of a molecular orbital. So because they are not of same symmetry. But if you bring it here, yes, they are same symmetry. Head-on overlapping is possible to form a sigma bond. Right? If you bring it it here, yes, it can. Head-on overlapping is possible to form a sigma bond. But if you bring it here, it cannot. They are not neither lateral overlapping nor because this orbital, s orbital symmetry is something else, p orbital symmetry is something else. So you need to orient them properly. Proper orientation of both the atomic orbital has to be there to ensure effective overlapping to form stable molecular orbitals. So now with this, I have discussed everything. One more point I'll tell you. Let me go back to quickly to these rules again. We have discussed first one. I have made it clear in this diagram. Number of atomic orbitals undergone combination will be equal to number of molecular orbitals. Look at this. We have two atomic orbitals. They are combined. They will give you two molecular orbitals. One is bonding, another one antibonding. Bonding molecular orbital will be of low energy. I have written it here somewhere. Yes, energy of bonding molecular orbital will be of low energy and antibonding will be of higher energy. Then filling up of, now once you have drawn this molecular orbital diagram, the electrons which are there with respective atomic orbitals, now they will come to molecular orbitals. Now how to fill up those electrons in molecular orbitals? What are the rules we are going to follow while filling up of electrons in molecular orbitals? So those rules are, all those rules we follow while filling up of electrons in atomic orbitals. Exactly same. Shall I ask you, can anyone tell me what are the rules we follow to fill up electrons in atomic orbitals? Can anyone quickly tell me, please?
Hund's rule.
Yes.
Pauli
Yes, very right.
exclusion principle.
Yes, very right. Another one?
Off-burst principle.
Yes. Off-burst principle, Hund's rule, Pauli's exclusion principle, all those three principles what we follow while filling up of electrons in atomic orbitals, all those we are going to follow here also. There is no difference absolutely, right? So we'll see that one by one. Let us pick up. This was a general example how to draw molecular orbital diagram considering atomic wave functions. Now we are going to see specific examples in our syllabus. We are going to discuss molecular orbital diagram. I'm writing MO diagram of homonuclear diatomic molecules. Homonuclear diatomic molecules, right? And heteronuclear diatomic molecules, both are there. We will try to cover it today. If not, we'll meet some other time, maybe tomorrow or day after, but we'll finish that. Molecular orbital diagram of homonuclear diatomic molecules. Very important, let me tell you, and very easy to draw also once you are convinced. No need to remember these diagrams. Once you are convinced with this, you can sketch diagram at any moment wherever you are asked. And let me tell you, it's very important for competitive exams also, if you are appearing those exams with chemistry as subject. That will be, that's why I'd invite your attention here. So let us start with MO diagram. The question is, let us say, draw molecular orbital diagram of hydrogen molecule, H2 molecule. Please follow the steps I am saying. Although this molecule is very simple molecule, but we are going to follow defined steps that will make more easier and it will make you understand better. So any molecule you are asked, homonuclear diatomic molecule. Just see what I'm saying, hydrogen molecule. So the question is, you are going to draw molecular orbital diagram from hydrogen for hydrogen molecule. So what are the atoms involved in that molecule? Hydrogen is one atom. What is its atomic number? 1. Write down its electronic configuration. 1s1. 1s1. That's the first step. What is another atom? Hydrogen, same atom. Do not worry, it may look simple, but you see, this is the procedure we are going to follow for rest of the molecule. You know, maybe heteronuclear diatomic molecule, homonuclear diatomic molecule like fluorine, neon, any molecule, we can draw with following similar procedure. So that's also, you write its electronic configuration, that same electronic configuration you have. Next is, you need to combine. We are going to write the molecular configuration. These are atomic configuration. Now we are going to write the molecular configuration of molecule, H2 molecule. Look at this. Now I will discuss the one by one the rules what we have discussed. The first rule suggests atomic orbitals of two different atoms. First atom hydrogen, second atom another hydrogen. It may be same atom, may be different atom, but at this moment, since we are discussing hydrogen molecule, both are same atom. Hydrogen atoms of two different hydrogen atoms. Atomic orbitals, that is 1s atomic orbitals of two different hydrogen atoms. What does our first rule says? Atomic orbitals of two different atoms of similar energy and similar symmetry. Now look at this. 1s, 1s. Obviously, both will be same, right? It will be, since both are same, they will be of same symmetry and similar energy. Similar symmetry and similar energy. Undergone linear combination to give you molecular orbitals, right? So head-on overlapping will lead to form sigma bond, right? So I'll write, they will give a number of atomic orbitals undergone combination will give you number of molecular orbitals. Since two 1s atomic orbitals are combined, we will be getting two molecular orbitals. Since these s orbitals are having sigma symmetry, they will lead to a head-on overlapping, so we'll be getting sigma bond. So let me write this. Let me get a symbol for sigma bond. We'll be getting sigma 1s. Let me write it like this, sigma 1s. That's bonding. Bonding will be of lesser energy, so it will be written fast. Another is sigma anti-bonding. Remember, this sigma anti-bonding, sometimes you'll find people are writing it as sigma A.
बच्चे अलाउ
H
करने के लिए कह
superscript.
रहे हैं
Yes, please. Anyone? Yes,
सर
please.
स्टूडेंट्स को अलाउ कर दो
Oh, okay. Some students are trying to enter. Oh, okay. Oh, yes, yes. Right. Thank you. Anyone who drawn my attention. So you look at this. Sometimes in some books you find it's written as sigma anti-bonding, or sometimes you'll find it's written as sigma star. It's just a star. Right? Remember, if you're writing a sigma A, then we write it's B here. You'll find sigma B. What does it suggest? Sigma and bonding, sigma 1s molecular, sigma 1s molecular orbital, that is bonding molecular orbital. The sigma 1s molecular orbital, that is anti-bonding molecular orbital. Or else, what we write? Let me write it, like this. Some people or they write it like this, nothing, B or A, just they put this star symbol. So either of the ways, feel free to use the notations, sigma 1s B, or if you are writing B, then you write A here. If you are not writing anything on bonding, then you have to put a star on anti-bonding. That's it, right? Now next is, how many electrons you have in total? You have to sum up the electrons. One electron from one atom, another electron from another atom. So how many electrons you have? 2 electrons. Now you have to fill up. You have total 2 electrons in your hand. You have to fill up them in molecular orbitals of hydrogen molecule. So what to do? Remember, which rule you will be following? Of-O principle. Of-O principle says a molecular orbital having lesser energy will be filled fast. Which one is of lesser energy? Bonding is of lesser energy. So it will be filled fast. So I'll be writing this configuration. And no electron, only I have 2 electrons, all are filled up here. So I do not have any electron left to be filled here. Second, Pauli's exclusion principle. Since this is not a degenerate set of orbitals, we are not going to apply Hund's rule here. Third rule is Pauli's exclusion principle. Yes, we are going to follow this. The two electrons which are there in sigma 1s molecular orbital, they will remain in antiparallel form. Now allow me to draw the diagram quickly. I will take this. What you have to do, this is one. Another side, let's say, just this one. This side you have one hydrogen. You write it, one hydrogen. Another side you have another hydrogen. Just match it with your whatever you have discussed. Just see. Next to this, whatever we discuss now, I'll give you certain molecules to draw at your own home. Then you will understand it better. Then you write atomic orbitals, 1s atomic orbitals. S atomic orbitals. Write down its configuration. Oh, okay, I'll write it. Okay, we can write it 1s1, and then another electronic configuration you write of another atom. Right. Yes. Now both you are combining. Two atomic orbitals you are combining. You will get two molecular orbitals. Right. And I will quickly connect them. They suggest these are from this. Atomic orbitals are combined to give you these molecular orbitals. Right? And now I will write sigma 1s. This orbital will be sigma 1s. Just wait, someone is trying to enter. Yeah. All right. Sigma 1s. This is bonding molecular orbital. And we have anti-bonding. What you would like to write? Star? Anyone? Let us write star here.
Yes, sir.
Anti-bonding. Yeah. Sigma 1s, sigma 1s star. I hope it is clear to all of you. This is 1s1 of one hydrogen atom, 1s1 of another hydrogen atom. Then you are combining them. You are getting two molecular orbitals. One is sigma 1s bonding. Another one is sigma 1s anti-bonding. Now you have two electrons. Let me draw it quickly. Allow me some time to get a drawing for electrons. One electron here of 1s1, another electron of another 1s1. Now we will be filling up. We have two electrons in total. We'll fill up it now. Both will be, since sigma 2s, it will be two electrons will be there. So both will be in, a flow principle is followed. while filling this orbital. Now, another electron you are filling off, so you need to follow Horn's rule. Quickly, let me draw an electron for they will remain in antiparallel spin. That's what your Offo principle says. Sorry, Pauli's exclusion principle says. Yes, that's what the configuration is now. Right? Now, using this, what this diagram, this is the diagram. What this diagram suggests. Look at this, another very important point I'd like to point out here. I have said it here. This is center of gravity or called barycenter. From here, what is happening? The amount of energy, see psi bonding molecular orbital is of lower energy. Lower means there is a lowering of energy. Certain extent of energy is lowered down, and that similar extent of energy will be increased up. So this deviation is same. Remember, you can't. That's why I'm making it very clear. It's not about making the diagram how it looks beautiful, but you see there is a fundamental behind this is this deviation from center of gravity towards up and down will remain same. Why? The amount of energy lowered down for bonding molecular orbital, similar amount of energy will be increased up for anti-bonding molecular orbital. Then only the whole molecule will be stabilized in context of energy. That's the purpose I wanted to convey. So same thing we are doing here. No need to invest good amount of time in putting scale and measuring these things, but try to keep it in mind. There is not, if you measure now, it may not be very correctly drawn. But the idea I'm trying to make you clear is that's the idea. So what are the other informations you are getting? This molecule, in this hydrogen molecule, since both the electrons are in paired form, so this molecule is diamagnetic molecule. It's a diamagnetic. This suggests from molecular orbital diagram, you can get, magnetic behavior. You can predict magnetic behavior of a molecule, which your valence bond theory was able to explain the paramagnetism of oxygen molecule. I have told you it's a part of limitations of the theory. But this molecular orbital theory is going to explain you all properties. This magnetic behavior is going to explain you fully, correctly. Second part, what we are going to get is bond order. Bond order. Can anyone tell me the formula for bond order? How can you calculate? Quickly, please. Anyone?
Number of electrons in bonding orbital minus number of electrons in anti-bonding.
Very nice. Number of electrons in bonding orbital minus number of electrons in anti-bonding orbital. Yes, then?
Divided by 2.
Yes, divided by 2. So now what number here? Can anyone tell me? It's equal to? Yes, what will be the number?
1
2 minus
minus 0 by 2.
2 minus 0 by 2.
2 minus 0 by 2.
And that's equal to 2. Is it 2? 2 minus 0 by 2 is equal to 2?
1.
1.
1, sir.
1. Okay. It's all right. So bond order is 1. That means there is one, sigma bond between hydrogen atoms in hydrogen molecule. That's what. So in examination, if question is asked to draw a molecular orbital diagram, you draw like this, and to calculate this bond order and these things. Other informations also you can get. Let's say we'll talk about hydrogen molecule and we'll ionize this. Remember, this is very important again. We will see hydrogen plus. Plus means what? One of the electrons has been removed. Now, which electron will be removed? And how are you going to remove these electrons? See, by incidenting a beam of light If that energy of that incident beam of light is greater than the binding energy of this electron, then this electron will be ejected and you will be able to get H2 plus. So H2 plus, the configuration will be, if I write H2 plus, the configuration of this will be this one. What will be the configuration of H2 plus? Anyone, please? Can anyone tell me?
Sigma 1s1.
Yes, that's it. Just I am telling you these things. Later on, we will come across certain problems. They are numeric to compare molecule and its ions to understand their bond strength, bond length. So for that context, I am making you familiar with this. Otherwise, if the asked to draw a molecular orbital diagram, that's how we'll be doing. The next task is to draw molecular orbital diagram for helium molecule. Quickly we'll move. So MO diagram for helium molecule. I would expect you also draw with me simultaneously. Can anyone tell me what is the first step we will be doing? Anyone, please? What is the first step?
Configuration.
Configuration of one helium atom.
Yes, sir.
How many electrons you have in helium? How many electrons are there in helium?
2.
2 electrons.
2. So, what is the electronic configuration?
Sigma 1s2.
No. Don't jump. That is why I'm saying follow the steps. Atomic configuration you are writing. So 1s2. There, students commit mistake. Remember, I understand that this molecule looks simple. That is why you are doing. But if this way you jump, there is a chance of committing error in higher molecules. Although not, if not in simpler molecules, there is a chance you will be committing error if you jump like this. As you increase the atomic number, so the higher molecules will be getting, heavier molecules will be getting. These are lighter molecules. For heavier molecules, you will commit mistake. So this one. The next is you write helium-2. You can, just to avoid confusion, you can write the number of electrons here. It's helium. So what we'll be writing, let me get the symbol from here so that we can. Same principle you apply. Two atomic orbitals of two different atoms having similar energy and similar symmetry are undergoing linear combination to give molecular orbitals. Number of atomic orbitals undergone combination will be equal to number of molecular orbitals. Symmetric combination will give to bonding molecular orbitals. Dissymmetric combination will give you anti-bonding molecular orbitals. Bonding molecular orbital will have lesser energy. Anti-bonding molecular orbitals will have higher energy. Already we have discussed in previous slide in detail. So that's why just I've covered in lesser time. So that's how the configuration would be. Now, how many electrons we have? Quickly, please. In total, 4. So 4 will be distributed now as per of principle. We'll be writing 2 each. So I'm not taking much time. I'll copy this diagram for you. Quickly, allow me some time. I'll copy everything so that at the lesser time we can finish it. Right? So what is the atom on this side instead of hydrogen? It's helium. Right? Helium on two sides. Helium. What is the configuration? It's 2. This side, it's 1s2. write down, let me pick off this. Electronic configurations. Right? We have 4 electrons in total. So 2 are here as Bravo principle and 2 will be there. Yes, that's the electronic configuration. That's how you're arranging. Right? So then same things you can do. This will be, what will be the magnetic behavior? It will be a paramagnetic molecule. Paramagnetic. Anyone? What will be its magnetic
Yes, sir.
behavior?
Paramagnetic.
It will be paramagnetic.
Anyone,
please?
No unpaired electrons.
Sir, diamagnetic.
So
Diamagnetic.
Yes. Yes. He was drawing your attention by deliberately writing this diamagnetic, and the bond order you can calculate, it's 0. So helium bond is non-existent. That's what it's saying. Next, quickly we'll move to draw molecular orbital diagram of next molecule. That's lithium. Let me see who is coming. Yeah. Lithium. Yes, can anyone tell me what is the steps to follow? Quickly, please.
Configuration.
Lithium 2. Lithium configuration will be writing how many atoms, how many electrons. Lithium 3 electrons you have. Although we do not write electronic configuration like this, 3 as superscript, but just to avoid confusion, we are doing it here. 1s 2 and 2s1, right? And same another atom you have to write its configuration. And we'll be writing configuration for lithium 2 molecule. Lithium 2. Lithium 2, what we'll be writing. Now you should look at the rules I'm going to explain. Atomic orbitals of 2 different atoms having similar energy and similar symmetry. Look at this. These are the atomic orbitals of 2 different lithium atoms. That's fine. Second part. Atomic orbitals of similar energy and similar symmetry. Now I will first pick up this one, 1s. 1s atomic orbital of 1 lithium will combine to orbital of which orbital of another lithium? You have 2 choices. 1s is there, 2s is there. Getting my point what I'm saying? We'll start from 1s. 1s of 1 lithium will combine with orbital of which orbital of another lithium? There we need to apply. It should be of similar energy and similar symmetry. Look at, just wait. We have 2 options, whether 1s or 2s. With which orbitals among these 2, the 1s of lithium will be combining. So now let us talk about this 1s. 1s, you have similar symmetry. Okay, that's fine. 2s also similar symmetry because both are s. They can have head-on overlapping. It's all right. So similar symmetry part is okay. Next part, energy consideration. Do they have similar energy? Let us check that. 1s. 1s is having similar energy with 1s of another lithium atom. 2s is of higher energy, so it cannot combine. So that's why I'm underlining this. Atomic orbitals of 2 different atoms having similar energy and similar symmetry, they will combine. You cannot combine atomic orbitals of your own choice. You'll pick up one s of one lithium of another lithium. You can't do that, right? So let's write the configuration now. Quickly, I'm not writing the electrons now. So 1s and 1s will be combined. How many molecular orbitals you'll be getting? 2. Both will be giving sigma 1s and sigma star 1s. Next, 2s will you combine with which orbital? You have another 2s left. And 1s it can't be, because although it is having similar symmetry, but 1s will be of lower energy, so it cannot combine, right? It cannot combine. So write this configuration again, what we'll be getting. Right, so it will be sigma 2s, sigma 2s star. That's the order, right? Now we'll draw this diagram quickly. Let me take this from here. Friends, remember, you cannot copy paste. I'm doing it here. That's why I'm writing the exact steps. But it will save time. That's why I'm copying it and pasting it here from another diagram which you have already drawn, which will save our time. So lithium, 2 different lithium atoms you write. 1s, 2, 1s2. That will give you sigma 1s, sigma 1s star. Next, we'll be drawing. Let me remind you what we have drawn. It's just energy. Let me go back here. Energy. 1s and then 2s is coming. Energy is increasing. That's what, right? 2s and another 2s. Another 2s. Quickly. Yes, another 2s. And what are the orbitals? 2s orbital. See who is trying to. 2s orbital. What is the configuration? 2s1. So we'll be writing this on other side. This one. Take it a little bit higher, because this orbital will be. Yeah. Just I'm providing space for better drawing, nothing else. So these 2s orbitals will be combined to give you 2 sigma 2s and sigma star 2s. Yes. Now I will combine them. Right. So 2s like this, and then yeah, we'll be writing 2s. Okay. Sigma 2s star. Sigma 2s. I'm writing here, Just, yeah, this one, sigma 2s bonding, right? Now you will fill up electrons. What is the configuration? Let us 6 electrons. You fill up 2 electrons here, then 2 electrons here, then 2 electrons here, right? So you fill up them accordingly. One, 2 electron here, right? Another 2 electrons here. Next I'm putting it here. Putting it here. Putting it here. No, you do not have electrons here. All right. So you have 6 electrons. Now you, what are you predicting? What about magnetic behavior? Anyone, please? What will be its magnetic behavior? In examination, question can be asked. Draw molecular orbital diagram of lithium-2 molecule and predict its magnetic behavior. Yes, anyone, please?
Diamagnetic.
It's diamagnetic or paramagnetic? It's diamagnetic. Very right. Diamagnetic. Very right. And bond order is
1.
1.
1. Bond order is 1. Yes. So that's how you go. So this is about this one, right? Lithium-2 molecule. Next is draw MO diagram. Quickly, I will finish with this example. Then I will give you task to draw. Beryllium, right? You draw on your own. Okay, I'm leaving this task for you. You draw on your own. What I want greater than this. I want to involve p orbitals. That's my purpose. So you draw beryllium on your own. I'm drawing boron, right? Quickly, because this needs time to little bit explain more, and this needs space also. So let me. Is it visible? This is visible. Is it visible? Because I have reduced the size of this. Yes, please quickly tell me what is the steps. 5. I'm not writing 5. It's confusing. So 1s, 2, 2s, 2, 2p, 2p x, 2py, 2pz, right? So you have this one, okay? And then another boron you write right here. This is very important. That's why I have picked up this. Then I will give you certain examples to do on your own. Then we'll repeat it next time when we meet, maybe tomorrow or day after. We'll find out the time. Boron 2 molecule. Now let us talk about this. Same thing, atomic orbitals of similar energy and similar symmetry. Atomic orbitals of 2 different atoms. Look at this, 1s. You have 1s. 1s of this boron will combine with which orbital? 1s can combine with 1s. Okay. Similar energy. Similar symmetry and similar energy. 2s having similar symmetry but not similar energy. It cannot combine. 2px, it's not having neither similar symmetry nor similar energy. Look at this. It will be situation will be like this. It can't. Px and py orientation it's like this. It cannot combine. So neither similar energy nor similar symmetry. So it cannot combine. But if you look at pz, right? So that is having similar symmetry but not having similar energy. So it cannot combine. So only option left is 1s. So let me write it. Get it from here. Save time. Yes. 1s will combine with 1s. 2 orbitals will be getting. 2s will be combining with 2s. I'm not writing electronic configuration now. We'll write. Don't worry. Next point is about 2px. 2px will combine with what? 2py, another 2px, or 2pz. For that, allow me to draw a diagram for you quickly. Yeah. This is 2px, right? It's 2py, it's 2pz. Z, it's, oh, okay. Let's do it. Just wait for a while. Just think of this: two different, two atomic or two, boron atoms. They are atomic orbitals: px, px, py, py, pz, pz. Now we'll pick up this px. Px will combine with what? This, or this. So this will have, atomic orbitals. Look at this: atomic orbitals of similar energy and similar symmetry. Look at this. All are having similar energy. That part is okay, because degenerate set of orbitals. Now next point is similar symmetry. This px will combine with another orbital of similar symmetry only. This pz is not of similar symmetry. So this px will combine with px and py. And that will give you this lateral overlapping of these orbitals will give you pi orbitals formation. Pi orbitals. It will give you pi orbital formation. This px and py, they will combine to give you pi orbital formation. Can we extend it for next 10-15 minutes?
Yes, sir.
Anyone, please? 15 minutes I need. Okay, it's all right.
No,
Okay, sir. Thank you, sir.
We have received the link for other class.
Okay, don't worry. Just a symmetry part I'll tell, then I'll leave. We'll draw the diagram later on. So just wait for a while. So this sigma, these are there. 2px and py. Just let me tell you the symmetry part I want to consider here. P orbital will write like this. Okay, no. Okay, this is one p, another. This is one p orbital. Just let me delete this. This is another p, right? Both are of same symmetry, right? They will combine to give you bonding molecular orbital. That is pi orbital, because they will uh, undergo lateral overlapping. What is this? This one, lateral overlapping. So this will give you a bonding molecular orbital. Quickly allow me some time to draw it for you. This bonding molecular orbital, it should like this. You'll be getting, and two orbitals of same symmetry. Another. Let's say we are talking about disymmetry combination. Now this is one. I want to draw. Look at this, what I mean by disymmetry combination. This is what I will do, and then I'll leave. Look at this. One orbital is plus minus, another is minus plus. Disymmetry combination. Not are in same symmetry. So that will give you bonding molecular. Look at this. I'll take you back here. We have seen like this. Plus minus, but minus plus. Right? So that gives you anti-bonding molecular orbital. So in this case, how are you going to get? So just allow me some time, please. Very interesting and very important as well. They are not combining, right? Anti-bonding combination. It will give you a pi orbital, pi star. It will give you plus. Look at this. This was plus minus plus minus minus plus minus. This is anti-bonding pi orbital. So let me write it. How I will be writing this one? 2p x p, or we'll write 2p y. I'll write it as pi. Let me get the symbol for you quickly. Quickly, I will leave with this pi. Make all these in this one. This will be pi star. Excuse me. Pi star. Increase it. This is pi star. Anti-bonding. This is bonding. Bonding pi and anti-bonding pi star. Now the next part is the remaining Z. You must be thinking, sir, what about Z? Yes, the Z will give you, I am putting it here, 2pz will combine with another 2pz. Quickly, allow me some time. Quickly. Right, and that will give you sigma bond formation, you know, just it's like this, you know, it's disymmetric combination. This will give you anti-bonding, but whenever I have to reverse this, just wait. We will start from here again because it's not, time is not that one. So this, so it will form a sigma bond, right? So this head-on overlapping.
sir.
Yes, please.
सर टाइम टेबल के अकॉर्डिंग हमारी जो क्लास थी वो 9 से 12 होनी चाहिए एंड मैम सर वेट कर रहे हैं. कुछ बच्चों को कोई प्रॉब्लम हो रही है, उन्हें लग रहा है मैंने मैस क्रिएट किया है. सो प्लीज़ आप क्लास नेक्स्ट टाइम ले लीजिएगा.
हाँ, मैं ले लेता हूँ
ओके सर, तो आप अटेंडेंस ले
So
लीजिए अब.
with this, yeah, we conclude here. We'll meet next time. Okay.
यस सर.
Just wait. So, who is having next class? Physical science or life science?
फिजिकल साइंस सर.
Next class किसका? Physical
Physical
science.
science,
Okay, I'll
sir.
take the attendance for physical science. Can we meet tomorrow? Can we meet tomorrow?
CR,
You are
maybe
here.
give us the CR sir, he may answer.
Yes. I'm asking, can we meet tomorrow? I'm asking, Dibas may not be there. I'm asking students. I am not interested. Can we meet tomorrow? Everyone, I'm